This is a production of Cornell University.
Thank you very much, Natalie. So today I'm going to talk about climate change and air pollution, regional global analysis. And what I want to stress here is this is a integrated assessment type of work, and that basically means that you cannot do this work alone. So as you can see here, there is a large number of people involved in these results, and I think you should keep that in mind. So I work at the climate change unit of the Joint Research Center. Joint Research Center is part of the European Commission. That means we are doing research that should be policy relevant. So try to apply all these things that Natalie was talking about in terms of policy analysis. The talk, the outline of the talk is that I'm first going to introduce the concepts of air pollution and climate policies, and also how they differ and what they have in common. And then go to the role of aerosol on climate, start talking about the benefits and trade-offs of a 2 degrees centigrade climate scenario. And you might not know what a 2 degrees climate scenario actually means, but this is something that the European Union as a whole is pushing for, to limit climate change by the end of this century, 21st century, to globally maximum 2 degrees. And this 2 degrees is chosen because it's kind of considered to be a threshold above which things are getting a bit out of hand. And you'll see, in order to get there, you have to do a lot. And then, if time permits, I will give some examples of work we're actually doing, and that might be relevant for some of the people here in the audience. So I'll give a couple of slides on the new EDGAR-4 emissions database, on the work on the hemispheric transport of air pollution, and an application of our work for India and for China. I might also, just if there are a lot of questions in between, might skip some of these things. Let's see where we end. Okay, air pollution is in its essence deriving from our need for energy, mobility, and food that leads to the use of fossil fuels and also the use of fertilizers that in the end are creating these emissions, nitrogen oxides, NOx, VOCs, hydrocarbons, that means, sulfur dioxide and ammonia, as well as particulate matter, aerosol emissions. That altogether gives us air pollution, for instance ozone, aerosols in the air, also the effects of deposition, that then can affect human health or ecosystems. And once this pollution is actually getting too large, governments typically set targets or limits that should not be exceeded. And in order to actually reach these targets, most of the time we put devices on chimneys, on stacks, or on tailpipes of cars, catalysts, to reduce this air pollution. And the alternative, working really on structural measures, so for instance, changing the way that we're producing energy, or changing our behavior, taking public transport instead of cars, for instance, is not so much considered in air pollution policies. It's mostly just put something on top of a chimney to reduce the air pollution. Climate policy, however, has a lot of similarities. It starts from the same need for energy, mobility, food, and fossil fuels, fertilizers, which then lead to the emissions of greenhouse gases. The most important ones are carbon dioxide, methane, and N2O, which then stay in the atmosphere for a fairly long time, 10 to more than 100 years. And they start influencing, interacting with radiation coming from from space, which leads to a temperature increase. There is all kinds of responses in the Earth system, the land, and the oceans, ice, which then lead to this temperature increases. A climate policy would, for instance, be what I just talked about, trying to limit the temperature increase to 2 degrees. You might think also of other options. The way that these climate policies are typically thinking and working is through structural measures, so changing the whole energy structure, or trying to change our behavior, for instance, energy saving. Okay. Well, if you think of end-of-pipe technologies, that is typically not considered. There are some examples. For instance, the capturing of CO2, carbon sequestration, it's called, is now also one of the options that you can actually do something about CO2. But it's going to be not very major. It might have a few percent contribution. Okay, so that is in contrast to air pollution policies, not so important in the classical climate policy. Well, if you want to integrate these policies, you see the drivers are the same, and then you have here the air pollutants and here the greenhouse gases. You want to see where these kind of things are being coming together. In addition, it turns out that some of the climate gases have also an impact on air pollution, like, for instance, methane is increasing globally ozone concentrations, and aerosols, PM, is on average thought to be cooling the global atmosphere, actually reducing the temperatures. Okay, and so you see there are a lot of things in common between these policies, and the art will be to combine these things. Well, what does that mean? Finding in each world region the right mix of technical, add-on technologies and non-technical control measures. And it has a lot of constraints because it should be socially equitable, so let's say acceptable to society. In developing countries, very importantly, it should not interfere with development and poverty reduction options, because if you're still thinking about your daily bread, you won't care too much about climate problems. So that is not trivial. It should be cost effective, meaning that the sum of these two hopefully will cost less than those two separately. And of course, it should reduce the effects of air pollution and avoid dangerous climate change, because that's why you started in the first place. Well, let's go back a little bit what we know about climate change. This is a figure coming from the IPCC fourth assessment report, which was published 2 years ago. You see the temperature going from the year 1860 to the year 2000 in the northern hemisphere and in the southern hemisphere. And this is actually not the temperature, but kind of the envelope of the temperature, normalized with the temperatures from 1960 to 1990, this period here in the northern hemisphere. So this is the zero line, and then you see that it goes from minus 0.4 to roughly 0.7 nowadays. Okay, and you see also in the northern hemisphere a relatively stable period, then followed by an increase, then again relatively stable, and then in the last two and a half decades really picking up again. And this signal is similar in the southern hemisphere, but this kind of stabilization, you don't see it so strongly in the period 1950 to 1980. Well, some remarks about this. The temperature trend that you see here, so globally roughly 0.7 degrees, a bit more on the northern hemisphere than on the southern hemisphere, does not match our expectations from what greenhouse gases alone should be doing. It should be more. And you see these differences in northern and southern hemisphere. And we think that at least partly these issues are related to this net cooling effect of aerosols. Okay? And of course there are different ways of looking at climate change. I think this is an interesting one here. But I will not go too much into detail here. Okay, how does it work? If you would consider the effect of CO2 alone, and you would have here the pre-industrial time, say 1800, here is the year 2000, here is the year 2030, we would expect now a global temperature increase of roughly 1.4 degrees centigrade. Okay, I just show you that what we have seen thus far is maybe half of that. And that is probably to a large extent due to this cooling effect, the screening by aerosols that reflect light back into space. Yeah? So if we would go on from here to now and then into the future, probably we would have not such a strong temperature increase. But what is happening now worldwide is that we're working on air pollution controls. We have already seen a fair amount of air pollution control in Europe, in US, and Japan, and we expect that also in developing countries, people will have to do something about the really very large levels of pollution, which basically means to a large extent that we're taking out a lot of this reflecting aerosol out of the air, which would bring us, rather than on this trajectory, temperature trajectory here, on such a trajectory that is more similar to what the greenhouse gases alone would be doing. Okay? And we have been trying that. This is actually a figure that Sylvia Klooster calculated, who is here in the audience. So this is what you get when you put this into a climate model. This is the temperature difference globally and annual average between 2030 and the year 2000, which would, if you would translate that from what Sylvia has been calculated into a transient response in roughly 0.6 degrees Celsius. Okay? And this is the picture that is arising, that if you would take out to the maximum feasible extent possible all these aerosols, where you would see like a much stronger increase of temperatures, which is also very much found over the northern hemisphere. Okay? So some of this stuff seems to be explainable by putting all our knowledge into climate models, and you'll see this kind of north-south gradients. You see the strong response in the northern hemisphere. Okay, and going from here to here, this is basically what then a climate policy is having to achieve, limiting the temperature increase to 2 degrees. And one of the issues that we're actually facing with is this, this strong rate of temperature increase that we expect to happen in the next decades, and which is probably much larger than we have previously been experiencing. And that might raise some issues on, are we really able to adapt to such fast temperature increases? Okay. So, this is a bit the context. JRC was asked to work on some impact assessments of proposed climate scenarios, and also on the combination of these climate change scenarios and air pollution policies to inform post-2012 global climate policies. 2012 is kind of a magic year. The Kyoto Protocol will finish then, and people are now preparing what is after, and maybe now with the change of government here that that also the US will be aboard in a global treaty. The work I'm presenting here is informing the UNFCCC Convention of the Parties in Copenhagen next year, where a lot of these negotiations will happen, and the idea is that this is kind of background material that people can get kind of a feeling of what is going on, what should be done. So, within the JRC, we have a group of people that are running energy forecast models, general partial equilibrium models, that is really looking at developments of the energy system depending on demand and amounts of fuels that are available, regionally differentiating, GDP growth, population growth, all these things are factoring in and are then leading to increased use of fuels. Okay, these patterns of energy and of CO2 emissions are then being fed in our global emissions database, which is called EDGAR. You see the EDGAR database is calculating air pollutants, spatially disaggregated and for almost all components that you can think of. Those emissions we then use in our chemistry, transport and climate models like the TM5 model and the ECHAM model to calculate air pollution. And from there you can go to impacts on all kinds of aspects, human health, climate, etc. 4 scenarios I will present today 4 scenarios. We have done, of course, more, but these are the 4 extreme scenarios. A business as usual scenario where energy is growing as it does now, air pollution is growing as it does now, no additional measures are being put into place, and that is of course almost a worst case scenario, if you would, but it's useful to illustrate. Then on the other edge of the story is the climate policies, mainly working on reducing the greenhouse gas emissions. Here are the air pollution policies. Without considering greenhouse gas emissions, they try to reduce air pollution. And the 4th scenario is where things are being combined. Okay? And we look at impacts on agriculture, natural ecosystems, human health, and on climate. And today I'm going to talk only about the latter 2 aspects. To give you a feeling of what it all means in terms of greenhouse gas emissions, I show you here the CO2 emissions that are associated with these climate scenarios. You see here, if we keep using energy and each year more worldwide, we are nowadays using about 30 petagrams of CO2 producing, which might increase towards the year 2050 to more than 50 petagrams. A climate scenario tries to bend this curve, so, well, starting to implement things now, we still have to face some increased emissions, and then after the year 2020, this should go down. So in the end, by 2050, going down by more than 30%. Okay. Translating this into air pollutant emissions, I give you the example of NO2 emissions. In the first case, the business as usual, here the yellow bar, we increase from 120 teragrams NO2 to more than 200, and then the climate scenario is following pretty much the CO2 emissions, here increasing to 2020 and then going down, so roughly in 40 years from now, we will still have the same global amounts. And this is a global picture, but there is regional detail behind this. Okay, and the air pollutant emissions, air pollutant controls would bring down the air pollutant emissions from 100 to 80, and then we assume by 2030 there will be no further policies into place. This is obviously a disputable assumption, but it would basically mean that the NO2 emissions would increase again as also CO2 emissions are increasing. Okay. Interestingly, I think is that with the two policies, you can actually globally reach about the same results. Okay? The level of ambition of air pollution control is roughly what Europe is thinking to implement by the year 2020. So by 2030, we think that worldwide, or we assume that worldwide, all pollutants are being curbed to the level of ambition as we have in Europe, which might be true for developed countries. It might be a little bit overly ambitious for developing countries. As I said, we have intermediate scenarios also that are treating these cases. So, yeah.
What about the case where you do both air quality and climate? You didn't present that.
I didn't present that here, yeah, but it's somewhere.
It should be lower.
It should be lower, yeah. So you put all these emissions into your model, and here I show you the calculated PM10 concentrations. PM10 means particulate matter, aerosol concentrations, and you see worldwide, if you look at PM10, it's pretty much dominated by natural emissions. Here you see the deserts, and here you see the oceans. Okay, and that is not really what we're interested in. We are interested in the anthropogenic part of this PM10 or PM2.5, and basically only a model can give you such a thing. If you go into the atmosphere, you measure everything together, and a model can actually separate these two things, and that's why models can be useful. So doing this calculation, you see that over the US we're calculating concentrations of 20 to 30 micrograms, a little bit higher here over Europe. But then the really high concentrations of PM we find over India and over China, sometimes reaching up to more than 100 micrograms per cubic meter. Now, how much is that, 100 micrograms? Well, this is a picture I took a couple of years ago in Guangzhou in China during a campaign, and this is corresponding to 70 micrograms per cubic meter of PM10. And I was told that this was not a particularly bad day, so it can be much worse than this. And you see that this is corresponding to a rather poor visibility. If you have calculated these PM aerosol concentrations, you can start thinking about what does it mean for human health. And this is interesting because part of the work is motivated by improving the air pollution situation, and you would like to know what does it mean. This is the change of statistical life expectancy for the business as usual case in 2030 compared to the year 2000. And you see a lot of geographical detail, say on average, or in the US, statistical life expectancy might go further down by 2 months. In the Middle East, 5 to 6 months, and even more in China and in India. And of course, I can show you plots for all these scenarios, but I tried instead to summarize that a little bit in this graph here, which is by itself also too busy, I realize that. But I want to pick out two world regions. So here you see all the world regions, and what I want to show you here is first the situation for the US, where you can see that if you do nothing, life expectancy for population between 30 and 70 years is going down by 2 months. Well, 2 months might not seem a lot, maybe not 2 months, but what is 2 months? If you multiply these 2 months by the population of the United States, which is about 300 million, then do it in your head. You see already that you get very big numbers, and divide by 12 you get years, and then we're talking about several millions of years of life expectancy lost. And that, in the end, in economical terms, is actually a quite important factor. Okay, so 2 months is probably a lot. And what can climate policy do? It can actually bend the curve, going from -2 to +2, so increased life expectancy. Air pollution policies by itself is more effective, but still the climate policy alone is roughly half of this. And combining these things is not completely additive, but still you see that these two policies combined will actually lead to a much stronger increase of life expectancy by almost 4 months. The situation in East Asia and South Asia, say China and India, is actually more extreme. I showed you already that the amount of aerosol in these countries is much higher, and that's also confirmed by measurements. But if these countries keep on track regarding economical development and population development, you see that there will be really strong decreases of life expectancy if this is going to happen without any additional policy in place. Okay, and this climate policy will actually make things quite a lot better. This is the green bar here. The interesting thing also is that only air pollution policy is and quite optimistic and stringent air pollution policy will not really lead to a lot of improvement. You see here it's still going down in Southeast Asia, in East Asia, and then what is interesting here is that really the red bar here, which is the combined policy, is the only scenario that can actually lead to an improvement by 2030 in terms of air quality. So I told you already, so interpret these numbers as they are averaged over the whole population and multiply it with the population, you get big numbers. And I show you here that there are large co-benefits of climate policy for air pollution, and probably also going to be large monetary benefits. And that's, of course, a very hard part to actually quantify that. But the numbers are going to be big. And in some world regions, climate change and air pollution policies are maybe going to be the only option to really improve things. Okay? So that is basically good news for climate policy. But there are also some trade-offs, and the trade-offs are in the climate system itself. And what I show you here is the calculated radiative forcing between 2000 and the year 2030, and first focusing only on the greenhouse gases. And I'm considering here ozone, methane, N2O, and the biggest one, CO2, of course. If you would have the business as usual situation by 2030, we would have an increase of CO2 forcing of almost, globally, almost 1 watt per square meter. And that's a measure of what can be the impact on temperature. Also, the other ones are increasing a little bit, so altogether this is probably going to 1.5. The climate policy is good, and it's doing what it's supposed to do. It's curbing CO2 emissions, and it's bringing down the CO2 forcing a little bit. Of course, the air pollution policy in this respect is not doing a lot, and the combined policy is roughly similar to what the climate policy alone is doing. The big impact comes from introducing the effects of, and the possible effects of what aerosols are doing. Because what is happening, if you implement the climate policy, you start, of course, phasing out the really inefficient technologies, the power plants that are not very energy efficient. And these power plants and other industries happen to be also the ones that produce a lot of aerosol emissions and aerosol precursor emissions. And that's basically what I want to show here. This aerosol, which in the business as usual case will actually lead to an additional cooling, is actually balancing some of the increases of the greenhouse gases in the business as usual case, leading to a total forcing that is roughly equal to what CO2 alone is doing. So here you see the aerosol direct effect, the direct scattering, and here you see the aerosol indirect effect, which is coming from cloud feedbacks, changes in cloud properties that can also lead to more scattering back into space of light. What I also want you to notice here that the uncertainty on this indirect forcing is huge. Basically, we have a fairly poor feeling of what the magnitude really is. And that is, of course, propagating in the overall uncertainty of what is happening between a few years ago and 2030. Now, taking out all these inefficient technologies is also doing something about the aerosols. So the net effect on aerosols is going down a lot, which in the end, if you add up by 2030 all these effects together, is not leading to a very different overall forcing by introducing a climate policy. Well, that is bad news, maybe. But look at this. Look at the effects of only air pollution policies. Here, this third row. You're really working on taking out the air pollutants very strongly, but at the same time doing nothing on CO2 emissions. And this overall forcing here is much larger than this climate change only forcing. And then taking these two things together in the fourth scenario is kind of an in-between result between these two scenarios here. So, in summary, there are these policies. People are thinking about that, proposing them, and to some extent actually achieving them. And we think that this reduction of greenhouse gases is really needed to avoid long-term warming, and long-term meaning by the year 2100, okay? And additional air pollution policies, especially in developing countries, will be necessary to do something about this very bad situation in terms of air pollution, so to avoid further health impacts. I showed you also earlier that these short and mid-term policies are expected in both cases to lead to a faster global and regional warming. And that's mainly because of this additional reduction of aerosols. But if you would do it by only looking at air pollution policy, then this warming will actually be much stronger, okay? And the story is not really complete, because I have been looking at 2030 here, and you should actually also look maybe at the 2100 time range. And then the story starts reversing, of course. The fact that you took out the CO2 emissions is really also avoiding climate change in 2100, whereas reducing aerosols now is more strongly working now and less strongly working in the future. And these kind of things are still not very well understood. We are working with greenhouse warming potentials, and now people start introducing greenhouse temperature potentials and trying to actually find the good metrics to quantify this kind of things. I showed you also large co-benefits of climate policy for air pollution mitigations, and we think that it's actually quite beneficial to start thinking about reducing air pollution by really structural measures in energy and in other sectors. And one aspect that I didn't really touch here, but it's to the heart of many people, is that the problem of this fast warming in the coming decades might be partly alleviated by focusing on reductions of short-lived warming agents, and those are, for instance, black carbon or soot aerosols coming, for instance, from diesel cars or biomass burning, biofuel use in households. Also, reducing methane emissions, which then in the end can also lead to lower tropospheric ozone concentrations and a lower forcing coming from this. Okay. I would like to continue with some snapshot results of research that is ongoing in the JRC. I'm going to give you some slides on the new EDGAR database, on gains and on H-step. I'll explain later what that is. So what is EDGAR? EDGAR is a database of emission factors and of activity data. And activity data meaning, for instance, the amount of cars driving around, or the amount of power being generated in coal plants. Okay, this database is mainly using international statistics, for instance, coming from the International Energy Agency or the Shipping Association, and there are many more sources here. It's looking at anthropogenic emissions. It's looking at the emissions of greenhouse gases, of photochemical precursors, and of aerosols. It's gridded, and the resolution in the EDGAR-4 database is going to be 0.1 degrees, so rather fine compared to what we have been doing before. It has a base year of 2005, working backwards in time to the year 1970, and it's supposed to be a reference data set for both science and policy. So basically, defining what the emissions are now might help us also to talk about where to put our money in reducing future emissions. Okay. The first set of results of this database have been very recently released, and we were expecting to have the full set online in a couple of months from now. It was a tremendous effort to do this. It's really tough work, and it took, of course, much more time than expected. But I think now there's going to be a very nice database that can be useful for people here who are modeling. Yeah.
What years? You say multiple years?
2005, and then going back to 1970, and maybe later we'll work back to also pre-industrial times. It's, the name you should remember is John van Ardenne, if you want to contact somebody. So it's going to be an online database. So there will be the option actually to really look below in several layers what is going into the final numbers that are coming out. And that has been typically a complaint of modelers who were using this type of databases, that they couldn't really see how the numbers were being generated. Well, this time I think it goes much deeper, and you can actually have a look at it. You can also start generating your own emissions if you think you have more local information than what actually went into this database. You can substitute parts of the database by your own things and try to improve things. So email, web address, you'll see it here, or you can send me an email. That's also fine. Okay, another example of work that we have been doing is working with people in India and in China to develop a tool for policy analysis of co-benefits of controlling air pollution and greenhouse gas emissions. So very much about what I was talking about before, but then applied to some really big countries and by consequence also really big polluters. Okay, using state-of-the-art models and then trying to make reduced form representations of these complicated models, basically linearization of the problem, because they need something fast. And if I run my model or Sylvia runs the model, it takes sometimes months to get the results out. And they want to have results in minutes, otherwise they lose the interest. And as a side product, we were also able to update the emission inventories for India and China, which then also flew into the EDGAR database. The useful thing coming out of the gains product is that it also produced scenarios, and these scenarios reflect often what the countries themselves think that the economic growth and growth in other sectors is going to be. And what this tool is actually very useful for is to show that if you do that and you don't think about air pollution or greenhouse gas controls, that things can go pretty much out of hand. Okay. Just to give you a feeling of how such a thing is being done, here is the TM5 model with a rather fine zoom over India in this case. And then you see India has a number of states and China has a number of provinces, and you start perturbing emissions province by province to see what is the impact of one province on the other. And the reason for this is that in these countries very often policies are not being implemented on a country scale, but rather state by state. So you need to show really to provincial policymakers what is the benefit of working together and doing something together on reducing emissions. And just to give you an example of how such a thing can be done, here you see Uttar Pradesh in India, where we apply an emission reduction over Uttar Pradesh, yeah, and then this would be then the resulting signal in this case in terms of change of deposition of sulfate, which is really extending much beyond the Uttar Pradesh itself. Well, these kind of things are then being put into this database. And you can reconstruct from this the overall signal. And you can also apply that to a scenario calculation. And this is actually the scenario calculation, which is an official Indian government prediction, a wish, if you would like. They would like to grow with 7% per year or maybe more. And if you wouldn't do too much about air pollutants, this is the resulting PM10, actually PM2.5 concentrations annual averaged. And these blackish colors here are 50 micrograms per cubic meter. Well, 50 micrograms happens to be the limit value in Europe, with the difference that it shouldn't be exceeded more than 27 days per year, and this is an annual average. So basically all days in India are above the limits in Europe, which are actually set such that we expect that health effects are not going to be too large. Okay, see, this kind of tool is of course tremendously useful for a policymaker to see what it means if you have your scenario as it is. Okay, I think in the sake of time I would like to stop here. I have some more slides, but you're probably all getting tired now. So I would like to go to my final slides, which is, thank you. Other questions?
Do you have analysis of specific technology combinations, or you're doing it sort of what if this happened? You don't have a sort of technology base underneath it?
Well, in the GAINS model, there is actually, GAINS is an optimization tool. So you really can attribute costs to substituting technologies by another one and finding that technology that should be substituted first in order to reach lower air pollutant concentrations at lowest cost. It's about money in the end.
So I'm particularly interested in, have you done an analysis of the difference between relying on liquid biofuels as opposed to plug-in hybrid electric? Because it looks as though Europe has figured out that maybe biodiesel's not all it's cracked up to be.
Well, I'm not really sure. This tool is not really my tool. It's being run at the IASA Institute in Austria. Here I gave you an example of the application over India and China. They also use it over Europe. I don't think they have done this full analysis for biofuels versus other fuels. I do know that people are very worried about well, the negative side effects of going into a biofuel technology. I think like also here there are stronger.
Not yet, but we'll get it.
Yeah, so we're finding more and more negative effects, which in the end might make you wonder if this is such a great idea. It's a difficult discussion, however. There are all kinds of factors, non-air pollution, non-climate related, that are also getting into the story, like energy security, like income to the farmers, and this will also come here. I'm sure about that.
Have these models been put in front of policymakers? I missed that. You're saying it's suitable for policymaking, but have they seen it?
The first part of the story is in direct collaboration with our policymakers in Brussels. Yeah.
And do they ever ask you about the uncertainty of all this stuff they're looking at?
They are worried about uncertainties, and then in the end they have difficulties to really do something with this. Okay, in a way, a policymaker is used to uncertainties, and a policymaker is balancing different uncertainties and then picks the one that he thinks will be most successful, not only in terms of the effects on climate in this case, but also in terms of feasibility. And he needs to. So it's not only this kind of uncertainties, but also just societal uncertainties that they need to balance. And in this sense, they seem to be able to work with this. Yeah.
And you, and this will be the last thing I say. Do you give them information that's probabilistic or something to do with uncertainty?
Well,
how to use it?
Well. Again, a difficult question, because I cannot read their minds how they're actually using it. You might have seen that on one part of the talk I didn't put error bars, on the other part I did put error bars, right? And I don't think that in the end that will dramatically change their conclusions, right? Basically you start with the realization that you need to do something about CO2 and that you need to do something about air pollutants, and there's probably no other way. So,
could you tell us what you would tell a policymaker those error bars meant? And were those two standard deviations?
Yeah, that is plus minus 1 standard deviation. Yeah.
Oh, so confidence interval would really 95 would be twice that.
Yeah. Yeah.
So how would you explain that to a policymaker?
They don't really ask too much about uncertainties. Yeah, but in reality, it's of course in the climate context, the real uncertainty is coming from the indirect effect, which is really the biggest uncertainty already for many years in this type of modeling. Yeah, so it can be much less, it can be also more, and yeah.
So I helped review the particulate matter regulations in the U.S.
Yeah.
Right, and we found that looking at the data, most of the changes were not statistically significant. And so I don't know. I'm not sure how confident you are in that. Given the U.S. 2-month increase in life expectancy, because we had a hard time finding statistically significant.
Yeah. Well, I mean, talk with the epidemiologists, and they sometimes tell you different things. So there seems to be schools of thought in this sense. What we have been using is a larger meta-analysis done by the WHO, and yeah, I think the uncertainties are large, but I think even if you would think like it's only 10% of what I showed you before, I think the numbers are still large, and maybe you should think also a bit in qualitative terms to look at this.
But you mentioned that in some regions, a combined climate change and air pollution policy may be the only way to improve air quality. So yeah. Can you elaborate more?
Well, what I showed you is that the fairly costly and fairly stringent air pollution measures that are planned to be implemented in Europe by the year 2020, applied to the situation in India and China in 2030, will, on top of this growing energy and growing activities, they'll not lead to an improvement of air pollution. So really what is needed is to do both, to combine these things, bring some of the really polluting industrial and energy producing activities down, and on top of that probably still also filter out what is being produced. Natalie?
I had a question about the aerosol impacts, and so you're using the ECHM results for this.
In part of, in the beginning of the talk, most of this stuff is done with the TM5 model, which was using a 2001 meteorology. Yeah, so.
I'm just thinking about the negative impacts of the aerosols and the release, the warming that happens there. From our discussions earlier today, so it seemed like the ECHM model is with minus 2 watts per meter squared, where it was pre-industrial current, which is bigger than the 1.5. That's the IPCC mean, is that right? So it's a little bit on the high side.
Well, these numbers were not produced with the ECHM in this case, but calculated offline, basically.
They would be more consistent with the IPCC.
What I've seen of it, it's relatively consistent, with the IPCC. Which is probably good enough for this type of study. You don't want to have a really extreme realization, although it can still be true, of course. It's, but that was not really the scope of this study too. I see two hands.
Yeah, so, all right. So I hadn't really appreciated how big an impact aerosols had in mitigating climate change. So maybe this is a dangerous question, but is it possible to create aerosols? That don't harm human health?
Well, it's interesting that you asked this question, because there is there are these geoengineering options. One was proposed by Crutzen to pump sulfur into the stratosphere, which would stay there for a year or more and cool, and cool then the atmosphere. Now, that stirred up a lot of discussion where things actually I have not really a strong opinion on if that is good or bad. Basically, I think in a way maybe geoengineering is even a possibility if you would consider that in fact we're doing already geoengineering by perturbing the system so much. There is another interesting paper in the Royal Society journal, which was really a bit funny, and I don't know if it can work, but that group proposed to bring on the ocean some kind of sailing boats with a kind of alternative sail. You might have seen the paper, and using part of the energy to actually pump up seawater and spray it into the marine boundary layer. And they argue that okay, this is not costing energy, it's seawater, so sea spray is around anywhere, and then they went to the cloud properties. It will change cloud properties and all good. I guess the challenge is in the technology, and well, it's interesting. They should maybe just start with spraying sea salt in the atmosphere with one ship and see if actually something is happening, I think, and then you can do step 2. If I were a rich man, I would actually sponsor such an experiment. So, yeah.
It doesn't go after the ocean acidification.
No, it's just pumping up seawater and cooling the atmosphere. It's not about acidification. No.
Any more questions? Let's thank the speaker again.